Gravitational waves are waves of gravity. I'm not exactly sure what you were expecting with a name like that, but that's what we got. Gravitational waves are ripples in the fabric of space-time itself. It is literal waves of gravity. And just like any other wave, like sound waves or water waves or electromagnetic waves, they have an amplitude. They have frequency. They have a speed. They can transport energy and momentum from one place to another. You can be hit with gravitational waves and you can feel it. I mean, not really because they're super weak, but I'm going to get to that later. I want you to think of gravitational waves in terms of how they wave and what they wave. You have to remember that in general relativity, our picture of how gravity works, space-time is a fabric. It's a dynamic, flexible, living thing. It's not that there's all these forces and energies and particles that sit on top of a fixed stage and do their thing. The stage itself is alive. The stage itself responds to the presence of matter and energy and can influence matter and energy. And that response and influence of the stretching and squeezing of space-time itself is what we call gravity. And so it was Einstein himself who first discovered gravitational waves. And of course he did, because he hogged all the discoveries and left nothing for anyone else. But, that's a different rant. But when he discovered them, he released a paper in 1917 saying, hey, look, gravitational waves. That's pretty cool, right? And then he immediately doubted their existence. And the reason he doubted their existence was that in order to get the solution of gravitational waves, in order for them to appear in the mathematics, he had to work with a highly simplified version of general relativity. The equations of general relativity are crazy complex. I mean, they're just a madhouse. They're almost impossible to solve. You have to make lots of simplifying assumptions to make any progress. And in one set of simplified assumptions, Einstein was able to arrive at the existence of gravitational waves. But he didn't know if this was a real thing or an artifact of the simplification process. It ended up taking decades, all the way until the 1950s, before we realized that, yes, gravitational waves are a real thing in the framework of general relativity. These waves of gravity are emitted from a variety of sources, and they flex space itself. They are not waves of time. You will not find any time dilation happening in a gravitational wave. Instead, what happens is, as a gravitational wave passes through you, you will get alternatingly stretched and squeezed. So you might get squeezed in this direction and pulled in the other, and then opposite, you'll get squished this way and stretched along your waist, and then back and forth, back and forth. That's one possible way for a gravitational wave to act on you. But no matter what, the action of a gravitational wave is always perpendicular to its direction of travel. So if it's moving through you in this direction, you're going to get stretched and squeezed in the directions perpendicular to that. Just like any other waves, there's an amplitude of how much you're getting stretched and squeezed. That's the amplitude of the gravitational wave. There is a frequency or a wavelength of how quickly these gravitational waves wash through you. And then there's a speed. The speed of gravitational waves is actually the speed of light. It's the fastest thing that could possibly be. And a good way to think about why a gravitational wave should travel at the speed of light is to imagine what were to happen if the sun were to disappear. Yes, it'd be miserable and everyone would die, but the physics of what would happen if the sun were to disappear. So let's say we're on the Earth, orbiting the sun, everything's great. And then in a moment, the sun disappears. Well, light itself takes 8.5 minutes to travel from the surface of the sun to the Earth. So we wouldn't find out about the death of the sun here on Earth for another 8.5 minutes. Like Mercury would find out first, and then Venus, and then Earth, because that's how long it would take for that signal to reach the Earth. Now, if gravity traveled instantaneously. Like if gravity happened like that, which in Newtonian physics, that's exactly how we thought of gravity in classical theories. Well, how would the Earth respond instantaneously to the lack of gravity? Well, it would go flying off perpendicular to its orbit, or tangent to its orbit. It would just go flying off into space without the gravity of the sun there to hold it. So how could the gravity of the Earth respond faster than the light signal coming from the sun? Gravity transmits information at the speed of light. And we can imagine if we were to make the sun disappear, there'd be like a brief ripple, a pulse in the fabric of space that would communicate the absence of the sun. Like dropping a pebble in a pond, you'd see this wave go out and it would wash over the Earth, and everyone on Earth would realize there's no sun. We wouldn't be in orbit anymore. We'd go flying off into space. Now imagine taking the sun, and instead of just making it disappear, of just waving it back and forth. What would that do? That would stir up space around it, and it would generate these waves that would just propagate outwards at the speed of light. And to make a gravitational wave is super easy. I'm doing it right now. Look, wave your arms like this. I don't care if you're like in public, just do it. Like wave. Look, you're making gravitational waves. Like the essence to making any sort of wave is to wiggle. You want to make a water wave? Go stand in the water and wiggle the water around. You want to make a sound wave? Wiggle your voice box, your larynx. That will make some sound waves. You want to make some electromagnetic waves? Take some charged particles like an electron and wiggle them around, and they will generate electromagnetic waves. To generate a gravitational wave, you take anything with mass and energy, which is all the things in the universe, and you wiggle them around. Any mass that's accelerating will generate gravitational waves. It's as easy as that. But gravity is by far the weakest force. By far. Like if gravity were a billion times stronger, it would still be the weakest force by a factor of a few billion. Gravitational waves themselves are tiny little perturbations, tiny little things on top of that already weak force. So it's a weak thing of an already weak force, and so gravitational waves are exceedingly weak. So you doing this is technically generating gravitational waves, but good luck detecting them. So to make appreciable gravitational waves, like serious gravitational waves, we need a lot of mass, we need a lot of energy, and we really need to make it accelerate really quickly. That'll generate super strong gravitational waves. So we're talking like black holes colliding. We're talking neutron stars colliding. We're talking supernova going off. We're talking supermassive black holes consuming clouds of gas and other stars. We're talking about the earliest moments of the Big Bang itself, where the whole universe is vibrating. This is the serious stuff that makes anything appreciable, anything decent when it comes to gravitational waves. And still, they are incredibly weak. And even those gravitational waves are incredibly weak, and we need some of the world's most sensitive detectors in order to spot them. Remember, Einstein first realized gravitational waves back in 1917. Then he doubted their existence, and he kind of waffled about it for a few decades, and then he died and stopped having an opinion on it. But even then, in the decades since, we're like, well, gravitational waves, yes, they might exist. It's a prediction of general relativity. But how do we do this? Enter the LIGO collaboration. LIGO stands for Laser Interferometer Gravitational Wave Observatory. I guess the W wave is not appearing in the acronym. Otherwise, it'd be LIGO. That'd be weird. So it's just LIGO. LIGO Observatory, seriously, these people took nearly a quarter century to get it to work. Nearly a quarter of a century of refining and building and expanding and testing and engineering a gravitational wave detector. We're like multiple scientists working over the course of decades to make this thing work. And LIGO is a masterpiece. It is what's called an interferometer. An interferometer is when you take a bunch of light lasers and bounce them off a bunch of mirrors and make it combine with itself. And you can either get the light to add to itself and you get like a really bright light at the end, or you can get the light to counteract itself and you make it go away. The point of an interferometer is it allows you to measure very, very, very tiny little differences. So like if I were to shoot a laser at you and you're holding a mirror and bounce it back to me and I don't get it into my eyeball and I make it interfere with itself. So like all the waves of the electromagnetic wave, all the waves of that laser line up against each other so everything cancels out. So nothing comes back to me. But if you shift just a tiny bit, like even like a nanometer or a femtometer, then the interference is broken just a tiny little bit and a little bit of light comes through and I can see that and I know that you moved your mirror. This is the essence of LIGO. They have these giant arms, like miles long arms, and two of them, and bouncing lasers back and forth, interfering with each other. And then they hang these massive mirrors and they just wait. They just wait. As the gravitational wave, as any gravitational wave passes through the detector, it will slightly change the position of these mirrors. It might bring the mirrors closer together, might push them farther apart, and that changes the interference of the light rays of the laser beam, and you can pick that up. It sounds easy, but like I said, it took 25 years to figure this out and to get it all right, because yeah, you have these hanging mirrors and the gravitational waves are like so weak that someone eating lunch in the control room is making so much vibration just from their like chewing that the detectors can pick it up. Or like a truck driving on the road a few miles away generates enough vibrations, or the seismic activity of the earth. So they had to spend 25 years, one, designing the technology needed to get the right sensitivity so you can pick up these tiny, tiny, tiny little gravitational waves, and 25 years understanding all the potential sources of noise and contamination so that they could dig out the actual gravitational wave signal. And in 2015, they did it. 2015 was our first direct observational evidence for gravitational waves. What LIGO witnessed was the collision, the merger of two black holes. And these were big ones. One was 30 times the mass of the sun. The other was 35 times the mass of the sun. They released enough gravitational waves, like the energy equivalent of gravitational waves was a few times the mass of our own sun. That is more power than all the stars output across the entire observable universe, all in the form of gravitational waves. These gravitational waves were strong enough that if you were within, say, a kilometer of the merger event, the gravitational waves would just tear you apart. But like I said, gravitational waves get very weak very quickly. You have to be like right up there in the face of the action in order to get anything bad. If you're just like 1,000 kilometers away, you're totally fine. You won't even notice. This particular event was 1.4 billion light years away. By the time the gravitational waves passed through the Earth, they moved these mirrors in LIGO less than the width of a proton. That's how subtle this effect was. And there are gravitational waves passing through this room right now and passing through that room right now. Like gravitational waves are constantly washing over the Earth, but they are so incredibly tiny, so incredibly weak. You need these insanely sensitive detectors to pick them up. And LIGO was able to do it. And they were able to do it because they knew what they were looking for. When black holes merge, they give off a very distinct fingerprint of gravitational waves. You know, as the black holes are getting closer together, they're stirring up space-time, generating these waves. As they get closer and closer, it gets faster and faster. So the amplitude goes up and up and up and gets faster and faster and faster, higher and higher frequency. And then they collide, and then the newly formed black hole vibrates for a while. We call this the ring down. And so we can see this very distinct shape to the gravitational waves that looks like nothing on Earth. It doesn't look like someone in the control room eating a snack. It doesn't look like a truck. It doesn't look like vibrations on the Earth. Seismic activity doesn't look anything like that. It looks exactly what we predicted it to look like from general relativity. That's how we knew we were spotting a merger of two black holes. And it's crazy to think about. The energy released is more power than all the stars in the universe combined, and yet by the time it reaches the Earth, it can't even move a mere more than the width of a proton. That's how weak these gravitational waves are. Gravitational wave astronomy is now a thing a few years later. There are two LIGO sites, one in Washington, one in Louisiana, and then there's a sister observatory in Italy called Virgo, working together with more on the way. They are detecting gravitational wave signals. So we've seen about 4 dozen confirmed gravitational wave signals from merging black holes across the universe and merging neutron stars, but that's my next video. This opens up a brand new window in astronomy, because the downside of gravitational waves being so weak is that they are weak and hard to spot. The upside, the good thing about gravitational waves being so weak is that they just pass through matter really without interacting at all. So if some distant thing like black holes at 1.4 billion light years away merge, those gravitational waves pass through galaxies, stars, interstellar dust without really getting absorbed, without really getting deflected, without attenuating, without disappearing, they just come on through. And then by the time we see it, we see essentially the exact same signal that was emitted by those black holes 1.4 billion years ago. So this is a very clean way to study the cosmos. It's a very pure way because it's not contaminated by all these nasty foregrounds in between us and the source. And because gravitational waves can pass through matter pretty much unimpeded, they let us see into the hearts of processes that normally we can't see. Like these two black holes that in 2015 that we first observed, there was no electromagnetic counterpart that we could observe. There was no flash, there was no boom, there was no bang, there was no nova. It was just two black holes in silence in the middle of space colliding. We would have never, ever, 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 ever seen that with traditional astronomy. But with gravitational wave astronomy, now we can. We're very interested in, say, how supernova work. Well, we can't see inside of a supernova as it's happening, but as it's happening, it generates gravitational waves, and we can see the gravitational waves. We can't see the earliest moments of the Big Bang because the universe was an opaque plasma, and we can't see that far. There's like a wall of fire preventing us from seeing the earliest moments of the Big Bang, but it released gravitational waves. And if we're sensitive enough and we can build the right detectors, we can pick that up. So this is something that we call multi-messenger astronomy, seeing the same event with different ways of accessing it through electromagnetics, through neutrinos, through gravitational waves. And also allowing us to see some processes in the universe that we normally couldn't see with traditional astronomy. Where will gravitational wave astronomy take us in the next few decades? It's impossible to say. We're building more ground-based detectors. We're building space-based detectors to get at more frequencies, further range, more sensitivity, just make it astronomy. Like 2015 with the development of LIGO was like Galileo's telescope. And he looked through the telescope and he saw amazing things, right? He looked at the craters on the moon, the moons of Jupiter, the phases of Venus. And then over the course of hundreds of years, we go up to, now we have like Hubble Space Telescopes and giant observatories. 2015 was gravitational waves, Galileo moment. And the future is going to be interesting and very, very wiggly. Thank you so much for watching. Please contribute to patreon.com/PMSutter. And I'll see you next time for more.